In this video, we will discuss the discriminant of a quadratic function and how we can use that to determine the nature of roots of a quadratic function. We are all familiar with the quadratic formula, x equal to negative b plus or minus square root of b squared minus 4ac divided by 2a. In this formula, b squared minus 4ac is called the discriminant. And that tells us a lot about the nature of roots of the quadratic function. These are the instances. Either the quadratic function will cut the x-axis twice and you have two distinct solutions, or the quadratic function, it just touches the x-axis at a point. So we say that it has repeated roots, or the quadratic function will not even touch the x-axis at all. So in this case, we say that it has no real roots. In this question, we are asked to find the values of k for which the quadratic function cuts the x-axis twice, touches the x-axis, and misses the x-axis. So first, let's compare the function y equal to k x squared plus k plus 3x minus 1 to the general form of the quadratic function, which is y equal to ax squared plus bx plus c. A is equal to k and c is equal to -1. It means that the discriminant of this quadratic function is going to be k plus 3 squared minus 4k times -1. If we expand this and simplify, the discriminant is going to be k squared plus 10k plus 9. So if it cuts the x-axis twice, then it means that the discriminant of the quadratic function is greater than 0. So basically, we solve the inequality k squared plus 10k plus 9 greater than 0. If we factorize this correctly, we'll get k plus 9, k plus 1 greater than 0. This means that the roots of this quadratic function are k equal to -9 and k equal to -1. We will use the sign diagram to determine the set of values of k that will satisfy this inequality. So we have k to be -1 and k to be -9. First, we want to find the set of values such that the left-hand side of the inequality is greater than 0. So let's start investigating by taking any value that is greater than -1. I'll investigate with 0. We'll see that if we put 0 in place of k, then this is going to be 0 plus 9, which will give 9 times 0 plus 1, which is 1. So if we multiply this, we get +9, and +9 is greater than 0. It means that the set of values x greater than -1 satisfies the inequality. Now let's investigate for values between -9 and -1. I'll choose -2 because it is within this interval. So if we use -2, -2 plus 9 will give us +7 times -2 plus 1 will give -1. And this will result in -7. -7 is not greater than 0, so will not satisfy this inequality. Lastly, let's investigate for values less than -9. I will use -10 to investigate. If I substitute -10 here, -10 plus 9 will give -1 times -10 plus 1 will give -9. And if we multiply, we get +9, which is greater than 0. So it means that x less than -9 also satisfies the inequality. Pardon me, we are not working in terms of x, so I'll just change these to k. So it means that for a, the set of values of k for which the function cuts the x-axis twice are k greater than -1 or k less than -9. Since it is the same quadratic function, I'm not going to start all over. B, if it just touches the x-axis, then it means that it has repeated roots. So in that case, the discriminant is equal to 0. So k squared plus 10k plus 9 equal to 0. Earlier, we factorized this and we got k plus 9 times k plus 1 equal to 0. So when we solve this, k is equal to -9 and k is equal to -1. So the set of values for which the function will touch the x-axis are k equal to -9 or k equal to -1. Lastly, if it misses the x-axis, then it means that the discriminant is less than 0. So we have the quadratic inequality k squared plus 10k plus 9 less than 0. So we'll use the sign diagram to investigate for the sets of values of k that will make this true. When answering A, we already determined that the set of values that will make the left side of the inequality less than 0 is this, when k is between -9 and 1. Therefore, the set of values that will make the function miss the x-axis are k greater than -9 and k less than -1.